Okay, so we're going to start looking at the uh, LCD screen, which the API for this is much more complicated than the previous one. And once we understand how it will work, writing the API isn't complicated. Um, what actually is complicated here is determining first off what the I2C address is, and then also just understanding how the commands and what modes we're operating in. There's a 4-bit mode and an 8-bit mode. So there's a lot of different things that we have to kind of understand in order to get this operating done here. So first off, yours is going to look something similar to this. Um, the key thing I want to point out here is that this is actually an LCD. This is an old LCD screen, very old. Um, Quite frankly, it's not one that you would use nowadays, but it's cheap and it kind of suits our purposes for this class. Now, it says it's a 1602, which just basically means 16 characters wide, 2 lines long. So you got 2 lines, 16 characters, and you can even say "Hello World, Sunfounder," kind of thing, because there's other ones here. Um, and uh, what you can see though with this here, this actually consists of two important chips here. And when you look at one, you'll only see one of them, but on the back side, now mine's red, yours might be red, it might be black, it doesn't really matter. There's something that's mounted on the backside here. Um, and you can even see there's this little, I can't really scroll over to show you, but when I'm zooming in, there's a little chip there. Now that chip itself has its own data sheet that we're going to look at, but that is interfacing with this actual board. This board has another chip on it that is driving the LCD screen. So there's actually two chips here that we have two data sheets for that we have to kind of concern ourselves with. And the other thing that's kind of frustrating here is that when you buy it from a website like this, doesn't give me any information as far as what is the address for this device. And then if I go down here and do like the comments and okay, no data sheet, blah 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 and everything, and it's talking about uh, thing here, and then it's talking about the address here is 027, which is actually correct. But if you look on some comments here, it says here, for instance, that the address is 35, 3F, not 35. So what is it says the default address for the LCD is 0x35, and then it says it's 0x27 up here. Well, which one is it? You might say, okay, well, this is from August 27, and then you could probably see, maybe I could figure out the date here. But the point is it's not convincing on, well, which address do we have? And there's even another one here, the default here. And now it says, well, it depends on what type of chip you have, which is true. But it looks like it's the same part number for the chips. Well, that's where there's a couple ways you can go out and figure out what this is. First off, the first thing we can do is let's go ahead and look at the data sheet. This is the one for the chip that I have. Now it's a PCF8574 is what mine is. And yes, there is a T after mine as well. So there isn't also an AT. And so basically this is an 8-bit I/O expander for an I2C bus. What this means is that it's essentially taking something that normally would run in parallel and converting it to serial communication. So the chip we're going to be communicating with has got 8 bits that we're going to be changing, and these are all connected up to the processor here. And then instead of having to send those things in parallel, what I will do is I will send the I2 from the master. I will send a single byte of data in serial, and then it will convert that serial byte of data into a parallel thing of 8 bits. Basically, it's just chugging them all down the line. And technically, could we run this device without using an I2C? Well, technically, yes. We could connect up 8 pins to run this one device, because if you're talking about wanting to run this one device, without an I2C interface, you would need 8 pins to connect it up, because you'll need, when we get into the device, we'll actually see why you need 8 pins. Now, you can see here there's this A0, 1, and 2 lines, and then ground. Now, what that means is this is actually a chip that you can program this chip to be having, let's see here, 8 different addresses. And you set that by determining which one of these is tied to ground. Now, in this picture, it's showing them all tied to ground. That, however, is not the way mine is wired up. So if I scroll through this data sheet a little bit more, first off, we can see that pins A0, 1, and 2 are on pins 1, 2, and 3. So when I probed mine, I had it powered up. As a side note, you need 5 volts to power the LCD screen, but there is a 5-volt out on the board. So if you just, it's right by the 3.3 external. There is a 5.0 voltage as well. So you can pull 5 volts off the board as well. So I pulled the 5 volts off, powered it up. I didn't even care about the SDA and SCL lines. I just powered it up with ground and power, and then probed that chip that's on the bottom there where pin 1 was. And what I discovered is the way they laid out, SunFounder is the one that I have here, the way they laid out their board is they actually tied A0, A1, and A2 all to VCC. In other words, these are all tied to 5 volts or a logic 1. So if I scroll down even a little bit more here, we can kind of see, well, how do we determine what the address is? There's lots of timing things here. Well, if I just kind of do a search for address, if I could type it in correctly, and then just kind of scroll through here. Okay, slave address. Now this is here how we have the slave address. This is the least significant bit, so A0, 1, 2, 0, 0, 1, 0, and then this is whether you want to read or write. So in other words, there's 127 different slaves we could have connected because you have to determine whether it reads or writes here. So we don't want to treat these as the way this is. We don't want to worry about this read write byte right here. We want to look at these 4 here, and if I think of these 4 here, and convert this to decimal, if I think of these 4 here, that would be 1 plus 2 plus 4, which is 7. And then I think of these, well, there's only 3 here, but this one's always fixed at 1, and these are always fixed at 0. So this is 2. So the address would be 27 based off of my measurements that I made. Okay, well that's all well and good, but let's suppose that this was in a case and I didn't have easy access to being able to probe those address pins in order to determine out what the slave address is. So now I'm running into problems. How do I determine the slave address? Well, this is where we can turn back to the PSOC creator and actually create a program that's going to tell us what the address is. And first off, let's go to the top design here. All I have here is a single I2C. Make sure, when I first was trying out this program to double check to make sure it was correct, I forgot to change it from slave to master. So make sure that you have it in master mode. And I called it I2C. And generate your API as normal. Of course, to do this now, you have to have the power connected and the SDA and SCL lines. It skipped my build since I had already just recently built it. Make sure that all 4 of those pins are connected up correctly. And again, you want to be connected up to the 5 volt. And then what we're going to do here is we're going to go to my main.c program here. And I'm going to create a couple variables here. I'm going to create an unsigned int, and I'll do an 8-bit unsigned int float, and I'll just say that's not float, flag equal to 0. Because remember, we can get those flags back from these master send starts. And then what I'm going to do here is I'm also going to create an unsigned int 8-bit I, and I'm going to initialize that to 0. And this is just going to be my counter. because I'm going to actually have my for loop not go an infinite number of times. Now I'm going to first go ahead and start up my I2C bus, which is what I remember in a previous video I had forgotten to do. So I'm going to start my I2C bus, and then I'm going to do here I'm going to do a flag is equal to, actually I want to do it this way. Flag is equal to I2C master send start, and then I'm going to just do it I, and then it doesn't really matter whether you're setting it up in read mode or write mode. I just did the write mode, so write transfer mode, and then an infinite timeout. But now I'm not going to do an infinite for loop here. I'm going to start with this. I'm going to start now at I equals 1 and go for I less than or equal to 127, and then I plus plus. So basically I'm going to be cycling through all possible I2C addresses. And what I'm going to do first here is I'm going to say, well, if flag equals 0, because that means it was successfully able to start the device, I'm going to return just 0, kill the program. Actually, am I wanting to do it this way? Actually, I'm going to start, even though we've done 0 once already, I'm going to start at 0 again. And the reason I did that one flag is because we're going to fail, and so when you fail, you can't just do another send start. You actually have to do send restart, because I'm going to have a lot of failures here. So I'm going to send restart I2C, write, transfer mode 0. Okay. So what this is going to do is it's just going to try and put it in transfer mode. It's just going to keep, so basically it's going to keep polling the I2C bus lines and say, hey, is there a component at address 0 there? Okay, there's not. Is there a component at address 1? There's not. Is there a component at address 2? There's not. So on and so on. It's just going to check through all of the addresses. Now, it's not literally going to check through all the addresses, because once I have a successful one, because since I only have one device connected right now, once I have a successful start, it's going to have that flag being 0. And how do I know that? Well, let's go and look in the top design again here. And let's look at the data sheet. And at the APIs here. So let's look at this send start. So here are the return values. Now, we could look up what these are, like what numbers these are, but in general, this is the way the error values always start. This is going to be 0. This is going to be 1. This is going to be 2, 3, 4, 5, 6, so on and so on, as far as the error codes we get. If I get a 1, it's going to say bus is busy, nothing was sent on the bus, the attempt has to be retried. And it says the hardware sets the busy status after a start decision and clears it on a stop detection. Noise caused by the ESD or other events may cause numerous start conditions on the bus, and the hardware assumes the bus is busy forever and will not be able to recover from this state. If this occurs, the SEB needs to be reset by calling the stop and start functions, which is not true. You can actually call the restart function, because the restart essentially sends a stop and a start. So we don't actually have to do that. All right, but let's go ahead, click this OK. And then what I'm going to do here is I'm going to set this in debug mode on purpose. I'm going to put a little stop right there. Actually, I'm going to put the stop on the flag right there on the if statement. Okay. And then what I'm going to do is I'm going to put it in debug mode. And the reason I have to do this whole if flag equals 0, return 0, actually I made one mistake here. I need to stop it here. The whole reason I need to do this is so that if I don't use the variable flag for something, it won't do anything. Except one thing you can do also, because otherwise there's this optimized out that sometimes shows up. And basically what it's saying is that, hey, if you don't really need to know what the value of flag is, it's just going to kind of keep it, it's not necessarily going to restore it back in variable. It's trying to optimize everything so that, it just maybe will temporarily hold it in a register as opposed to storing it back in memory. Since we're basically using it in the next line of code for it. So that's when sometimes it says optimized out if you're doing a debug. It's because it's not actually going back into memory because the code recognized that, hey, I don't really need to store it in memory. I can just store it in a register temporarily and check it this way. But by doing volatile, it forces it to be stored in memory so we can basically inspect it all the time. All right, so now let's go here and do another debug on it. So now you can see flag is at 0 because it's saying, okay, we are definitely defining this as volatile, so it's definitely there. It even gives you the memory address of this is where the memory address is that it's located at. Now, I'm going to have it in hex format, and then I'll, no, I don't want this in hex format. Decimal format. Well, hex is fine. It doesn't matter. Let's just go ahead and put it back in hex. Doesn't really matter. All right, so I'm going to hit go down here. So I see I get an error code of 2. I thought I was going to be getting error codes of 1, but error code of 2. So what that means, master's not ready to start a transfer. Has not completed a previous transaction or slave operation is in progress. Nothing was sent on the bus. The attempt has to be retried. Okay, so I have to retry it then is what it's saying. Okay, but that was when when I was at 0. So I'm going to hit forward. Now I'm at 1. I'm still getting the same flag error. So it tried 1. Now it's trying 2. Same flag error. So I'm going to just cycle this through a little bit quicker because we know based off the data sheet that this should be 2.7. So I'm going to keep going forward here. And you notice that the error is still staying at 2. And now I should be getting here, if I do 6, and now on the next one here, when I execute this, the flag should now change to 0. And it does. That means it successfully sent a start command and put the bus in write mode to address 27. And again, since that's the only thing that's hooked up to the LCD, I'm sorry, the LCD is the only thing hooked up to the I2C bus. That has to be the address of the I2C device that's connected. So we now know for certain, based off both the data sheet and by just going through this loop program here, that the I2C bus is 27 for this. Now you absolutely should check by running this program here to make sure that your address for your LCD is the same, or it could be 3F is the other most likely candidate, or it could even be something else, but it's most likely either 27 or 3F. But you absolutely need to check to make sure to see which one yours is, because that's going to affect the rest of our programming when we start writing the API for this. And this is a good thing to have because, as I said, sensors sometimes they're not great at reporting all the addresses to you. And the data sheets can be sometimes really crappy and not only not giving you the address, but not even giving you any indication on what the address is. And so you just have to scan it. Now there's other ways to write other scanning programs for it, but this I think is the easiest way to scan it. There's another way. What you could have done is you could have, instead of putting it in a debug mode, you could have printed to like a serial screen. Like you probably printed hello world into the serial screens like when you were in your first C programming class. We could do something similar to this as well, so that we could just have basically a text file that's created and we could just kind of go right there and real quickly see which line it is that's the correct one. But this doesn't take too long. I mean, you're talking 127 at 128 at most. So this is the preferred method.